Greetings, let's continue our look into entropy. Well, today we're investigating entropy changes and predicting entropy changes that will occur during state changes and chemical reactions. So following very naturally on from the previous video, we introduced entropy as a concept, as a measure of disorder, really talked about what that means and the idea that the universe tends towards disorder. Entropy is always increasing because that's an energetically stable configuration for it to exist in. We're gonna keep exploring and start popping some numbers and looking at how these numbers can change through various changes that can occur. So to remind ourselves, entropy is given the symbol S. It's a measure of dispersal of energy at a specific temperature. So delta S is equal to Q, which is the energy in joules, divided by T, which is our temperature in Kelvin. We said it can be thought of as a measure of the disorder of a system, where an increase in entropy is an energetically stable form. In chemistry, we're talking about our systems being our chemical reactions. All based on the laws of thermodynamics that we went through, and importantly, the second law of thermodynamics is stating that the entropy of a system always increases. The universe tends towards disorder. Energy is constantly being transformed into less and less usable forms. The idea that no energy transfer is 100% efficient, there is always energy that is lost as a less useful, a less usable form. We were looking at some diagrams. We're looking at this idea, mainly focusing on the idea of diffusion to help us grasp entropy and disorder. So we're saying the diagram on the right-hand side is going to be more disordered than the one on the left-hand side, which is more ordered. So therefore, the one on the right-hand side there is going to be a higher entropy. It's going to have a higher value for entropy. One final idea we introduced is the idea that entropy is quantifying the number of microscopic configurations, the microstates you can call them, that are consistent with the macroscopic quantities that characterize the system, the volume, the pressure, and the temperature of the system. So we were thinking of these microstates predominantly with our arrangement of gaseous molecules, in a system where it can diffuse. These microstates can also be thought of with the amount and the types and the number of bonds that our particles can interact with each other through. And that's what we'll be looking at a little bit more today. So let's get some numbers on this. Let's compare entropy values. As always, to have a fair comparison, there must be standard conditions. And we've seen these standard conditions before, and we've given them this plimsoll sign. So we can have our entropy, or our change in entropy, at standard conditions. Just to remind you, our standard conditions are a pressure, which is, roughly 1 atmosphere of pressure, a temperature of 298 Kelvin, which is about 25 degrees C, and each substance involved in the reaction is in its normal physical state at these conditions, be it a solid, a liquid, or a gas. So from these conditions, we can state a standard molar entropy. So if we have entropy as the joules per Kelvin, the energy per temperature, we can get that per mole of substance and end up with a standard molar entropy. So S plimsoll, showing our standard conditions for S, entropy given the symbol S, and we have our units joules per Kelvin per mole because we're a molar entropy per mole. So here's a bunch of values that I'm just going to pop up on the screen here. Have a look at them. Take them in. Good numbers. Why don't you pause? Why don't you pause and look at those numbers? Look at the substance that we have. Look at what state it's in. Consider what bonding it has, and consider its entropy value, and really explore it. Why don't you see if there's any general trends that you might be able to infer from the values for entropy that we're given there. I'm going to say general trends because we're going to go through some real broad brushstrokes here, some real broad general ideas of how we can predict entropy values. But of course, nothing is ever that simple, is it? So we're talking quite generally here. So bear with me whilst we investigate these numbers. What do we notice first of all? The first thing that we might notice is that we have no negative values here. All our values are positive. Because entropy values are compared to a theoretical perfect crystal, we reintroduced the second law of thermodynamics just before, the idea that entropy always increases. We had the first law, which is, the conservation of energy, can't be created or destroyed. And then we had the third law of thermodynamics, which talks about all perfect crystals have the same entropy at absolute zero. So it's that idea at minus 273 degrees Celsius, all particle movement ceases. So that's the theorized lowest temperature that can exist. So at this temperature, all perfect crystals have the same entropy at absolute zero. So you can think, if you like, if we can say this, you can think of them being a perfectly ordered crystal. We can't reach absolute zero. And in fact, it might even be a sort of a theoretical if it can actually be reached by us humans. But that's neither here nor there, I digress. The nearest we can get to this is a perfect diamond weighing 12 grams, cooled as low as possible. And that's what we have here. We have the entropy, not quite zero, but look pretty darn close, 2.4, a very, very, very low entropy. A very ordered system is that diamond. Now, important thing, we're looking at entropy values, and we say that entropy values are all positive. Don't confuse this with a change in entropy, the delta S, where we can look at the entropy before and afterwards, where we can very much have negative delta S values. Same way we've looked at delta H values. You can have positive or negative delta H values. You can definitely have positive or negative delta S values, but if we look at sort of an absolute entropy of just a single species, they are going to be positive based on our laws of thermodynamics. What about the entropy of the different states? We have solids, we have liquids, and we have gases. And what you might be able to observe going down, generally, gases have a higher entropy value than our liquids. Liquids have a higher entropy value than our solids. We'll very much talk about why this is a bit later on in the lesson. But you can think of gases as being more disordered than a very structured three-dimensional solid lattice. So generally you'd expect a gas to have a higher value for entropy. You'd expect it to be more disordered than our solids would be. Of course, there are exceptions. I mean, we've even got exceptions on our list here. If I can very quickly find one, silver nitrate, which is a solid, has 140.9, but mercury, which is a liquid, has a lower entropy value because it's just one factor that is influencing. There are other factors that we can see as well. If we compare the complexity of the substance, meaning how many bonds can be present. Generally, the substances that have fewer atoms have lower entropy values than complex substances with more atoms. And this has to do with the idea that there are less microstates possible. So we said just previously here that entropy is quantifying the number of these microstates. So the less microstates that are possible, the more ordered it will be. The more microstates, the less ordered it would be. So like I was saying earlier, we were thinking of that in terms of diffusion, but you can also think of that in terms of the energy that's stored in bonds. So the more bonds, the more possible microstates can exist. Therefore, the more outcomes, all that good stuff that we looked at last time with the probability and the statistics. But generally, substances with fewer atoms have lower entropy values than complex substances with more atoms. If we compare, a argon, which is a single atom, we have a lower entropy than something like carbon dioxide, which is going to have more bonds. It's got covalent bonds, in addition to its intermolecular forces that the argon would have as well. Compare something like silver nitrate with its more atoms, more bonds, more microstates, the energy in those bonds can exist in. It's going to have generally a higher entropy value than something with less atoms. And then the final trend that we can infer from the data here is looking at substances, looking at the hardness of similar compounds. So we have a diamond carbon and we have a graphite carbon. The diamond being much harder, we can see that the harder it is, the lower the entropy value is as well. You know, we can compare our metals as well. Look at lead, which is a softer metal than copper. We can see that we've got a lower entropy value for the copper. And again, that's all to do with the kind of bonds that can exist between the atoms. So we can compare, we can make some general trends based on its state, based on its complexity, based on its hardness, and we can compare those values, compare them to infer if there is higher, lower entropy, more disorder, less disorder. Let's get into it. Let's look at some physical changes here. Let's begin with state changes. So consider heating ice to steam. Well, let's go back and let's think about what happens to temperature as we increase energy. So if you recall, it's not a straight line. What do I have to do? I've got to do that. So as you recall, hopefully, or maybe I'll remind you now, if you have the temperature of a substance, I don't need my straight line anymore. What am I trying to do? There we go, I got it. All right, let's say temperature down here, and let's say we're putting energy in. So as we increase the energy, so let's say we start with a solid lattice where we've got our strong bonds between our particles. As we put the energy in, those particles start to vibrate more in the solid form. So we have an increase in temperature as we put more energy in. But then once we get into the state change, we see that phenomena occur where even though we put more energy in, at the melting point, the temperature doesn't actually increase. It's not until the substance has completely melted that we then see the temperature begin to rise again to the point we get to the boiling point, and then eventually we have the gaseous state. I'm just going to extend my axes down the bottom here. What's my eraser? No, that's like a laser. What is that? Oh, laser pointer. Oh, sorry, I'm getting distracted. Let's extend our axes across here like that. Nope, not like that. Like that. Oh, look at that. Nice. So at our phase changes, the energy is no longer causing the particles to vibrate or causing the particles to move quicker. Instead, it's starting to break those bonds between the particles to get them from a solid to a liquid or a liquid to a gas. We can take this idea and we can extend it to look at entropy and how entropy changes in a substance as you put more and more energy into it. So we got our solid down there. Then we go into the liquid, then we go into a gas. So if this was going to be water, which is a good old example that you can't go wrong with, the melting point there is going to be at 100 degrees Celsius. Nope, it's not. It's going to be at 0 degrees Celsius. And then our boiling point here, this one here will be at 100 degrees Celsius for our example for water. So let's consider water and let's compare entropy values now. So consider heating ice to steam. The molar entropy of ice just below the melting point is 48 joules per Kelvin per mole. Molar entropy of water is 69.9 joules per Kelvin per mole. Molar entropy of steam just above the boiling point is 188.7 joules per Kelvin per mole. This is consistent to all we've been saying. If we've got the ice and the three-dimensional lattice, I can draw that a bit better. You know, we would expect that to be quite ordered, not as many microstates it can exist in compared to the liquid, where the particles are still bound to one another, but now they're able to move over one another. So there's more microstates, there's more positions they can exist in, and then our gas in our high kinetic energy, moving around very quickly, there's even more states they can exist in again, more microstates, so we have an even higher entropy value. So we can certainly observe that our entropy is increasing as we change the state from ice into steam. As you heat the substance, the particles vibrate more, thus increasing the disorder of a system because there will be a higher number of ways to arrange them. So we just did that. We compared our liquid and our solid and our gas. And if you think about in a solid, the particles are fixed in position. There's only so many microstates. In a liquid, they're now able to move, like I say, move over one another, but they're still bound to one another. So there's more microstates than the solid because of that movement. However, less than the gas where they can move and fill even more possible microstates. Interestingly though, we see the biggest increase in entropy at the melting and boiling points. And you might want to have a pause and think about that. And similar to how we've drawn previously a phase change diagram looking at how temperature changes when we put energy in, have a think and see if you can predict how the entropy is going to change as the temperature increases. You can draw that and then have a look at what we've got here now. So as we just said, we start in our solid phase. In our solid phase, as we increase the temperature, the solid, they're still fixed in position. However, they're able to vibrate more fiercely, gives us more microstates available, more ways to arrange them. If I get rid of my ugly mug there, and we can see under here, more ways to arrange them, so therefore a higher entropy. But what we observe at the melting point is the entropy increases sharply, but the temperature doesn't change at all. And we can think about why that is, because we've said here that at a phase change, the temperature doesn't change. So we wouldn't expect the temperature to change at a phase change. So that's why the temperature remains the same. We can see the value there is not changing, but the entropy is still increasing, and it's increasing quite a bit, because what we're doing is we're now breaking those bonds. We're breaking those bonds between the solid particles to get them into the liquid particle. So as they can move more and more microstates, higher entropy, more disorder, all that good stuff. But then once we have completely entered the liquid phase, we then observe the temperature increase. As that liquid temperature increases, as the kinetic energy of these particles start to move more and more, again, more ways to arrange them, more entropy, and we observe a very similar thing at our boiling point, where we don't increase the temperature stays constant at a boiling point, but now we're going from that liquid breaking those bonds to the gaseous phase, where there's even more microstates they can exhibit because they are not bound to each other at all. They're moving with that high kinetic energy. So these phase changes, when we're considering the entropy, we can refer to it as the entropy of fusion. So the delta S, FUS, to designate that it's the fusion. An increase in entropy when a substance is melted. So this is just summarizing what we were talking about before, but we'll put it in nice, concise sentences. It moves from a solid, which is a regularly arranged lattice, particles close together, fixed in position, less microstates than the liquid, which is a regular arrangement of particles. They're close together, but they're able to slide over one another. So many more microstates available in the liquid state. Disorder has increased. And we see the delta S of vaporization being very analogous to that. An increase in entropy upon vaporization of a liquid as the substance moves from liquid to a gas, and even more irregular arrangement compared to what the liquid was. Even more irregular, particles far apart, more moving with much more kinetic energy more rapidly. So we've got even more microstates, which means even more disorder. Just a couple of notes here. Dissolving, which is also a physical process. We see a similar thing, entropy change, occur with dissolving. When we dissolve, we tend to increase entropy because we're increasing those microstates. We can also think of these in terms of their sort of reverse process. So last time I told you that entropy can't be reversed, but you might look at this and go, hey bozo, if we decrease temperature, surely that's decreasing entropy. And the answer is yes, it is. But the answer is also no on a sort of the global scale, the global accounting of entropy. Because, you think about get an ice cube, pop it outside the freezer. the probability of disorder will tell you that that will melt, that will become warmer. There's an outcome where that you take an ice cube out of the freezer and the entropy increases. It actually gets colder. However, that outcome is so unfathomably small for all those reasons we talked about last time that the entropy is going to increase towards disorder, which is that ice cube melting. But entropy is very much dependent on temperature. We saw entropy as heat. What am I doing? Q. Too many Qs. We saw entropy as heat per temperature. So it's certainly dependent on temperature, where if we pop that ice cube back in the freezer, we pop that liquid that we melted back in the freezer, it's very much going to freeze again. It's going to go into the solid state, and that's going to decrease the entropy of that particular substance. However, on the universal scale, entropy is always increasing. So if you think about how you got that freezer cold to begin with, well, you've probably got that plugged into the wall, plugged into the socket, and that's using energy. Let's say that energy was produced from something like a combustion reaction. Well, we'll see in a moment, a combustion reaction very much will increase entropy because of the products that we get from that combustion reaction. So when we talk about entropy can't be reversed, we're talking on this universal scale. So these instances where we're decreasing entropy, there's always going to be a net increase in entropy somewhere else. You're just passing that buck down the road. You pop your water in the freezer to decrease the entropy of the water, but that fridge is being powered by a combustion reaction. That's very much net increase in entropy. So it always levels out to where the entropy is always increased. A little aside there, don't worry too much if that just confused you more, but just something I wanted to touch on. Brilliant. So that is talking about entropy and state changes, physical changes. Now we can get into some good stuff by looking at the entropy and how it can change with chemical reactions. A change that occurs naturally, i.e. by itself without outside assistance, is referred to as a spontaneous change. A spontaneous change is one that once it begins, once it commences, it will continue by itself until completion. So for example, if you've got a combustion reaction, if you've got your Bunsen burner, which I'll draw a little Bunsen burner there. Pretty good diagram, I know, a little safety hole there. We got the flame coming up. Look, I'll even get some color in. Woo! All right, you got your Bunsen burner. What happens once you start that combustion reaction? Well, that's going to keep happening spontaneously. This will keep running until you either turn the gas off. That's my little gas pipe coming in. Until you either turn the gas off and you stop the fuel going through to it, or until you stop the oxygen being available to it. But it will continue to react until one of the reactants run out. That's what we refer to as a spontaneous change. Not to get confused with spontaneous as, how we might use it in our everyday vocabulary. A spontaneous change most certainly does not have to be quick. Combustion reactions we think of being as quite a rapid reaction, but they can be very slow reactions. And they may need an input of energy to start them. Think about, the idea of activation energy. The important thing about spontaneous reactions and spontaneous changes is that once they begin, they'll keep going until those reactants run out. So many spontaneous reactions are slow, or they need an input of energy. You consider your Bunsen burner there. You can have the fuel and the oxygen running, but it's not going to commence until you start that process with that light, with that match, which is what I've drawn there, if you're wondering what that is. Changes that increase entropy are energetically favorable. The system becomes more energetically stable when it becomes more disordered, and this just feeds back into all that probability we looked at last time. So go revisit that one or watch that one if you haven't watched already, if you really want to know about why that is. But it just becomes this statistical likelihood of disordered outcomes being more likely than ordered outcomes. So changes that increase entropy are energetically favorable. In chemical reactions, we compare the entropy of the reactants and products by comparing what we looked at up here. The idea that generally a gas is more disordered than a solid. It has higher entropy than a solid. The more complex it is, the more entropy it will have. The harder it is, the less entropy it will have. So we can look at the reactants and look at the products. And if we see, substances that were going, perhaps solids on the left-hand side, on the reactant side, to gases on the right-hand side, that would imply that we're increasing entropy. If we look at, a very simple molecule going into complex molecules, that implies an increase in entropy. That implies it's getting more disordered, and as we keep on saying, that is energetically a favorable process. All right, so we can then infer if the entropy change will increase or decrease. So I've got 3 reactions here that I want you to consider. Predict if the following reactions will cause an increase or decrease in entropy, and do this by looking at the states on the left-hand side and the reactants and the states on the right-hand side. And remember, as it's going from solid to gas, if we have gaseous particles, we could predict it's a higher entropy than solid or liquid. So that would be energetically favorable if we're going from solids to liquids or solids to gases, for example. Look at the complexity. The more bonds that they have, the more microstates with the energy between those bonds that can be existed in. And then you can look at the hardness as well. So give a pause. See if you can predict if you're going to see an increase or if you're going to see a decrease in entropy. And rationalize it. Tell me why. And then you can pause and check your answers now. Calcium carbonate. A decomposition reaction. We would expect to see an increase in entropy. Now, this is just a prediction. This would be a good prediction. You would obviously have to get some numbers in there to know for certain, but we're just going based on these general rules we've seen. Why would we predict an increase in entropy? Well, because we've got a solid on the right-hand side, on the left-hand side. On the right-hand side, we've got solid, but we've also got a gas. And we've been talking about the idea that gases can have more microstates than solids can, more complex, more disorder, increase in entropy there. We also have, more complexity. We got more bonds. You can think about, inter and intramolecular bonds, or bonds between substances in the reaction. More bonds, more microstates with the energy in those bonds. If we compare that to good old Haber process there, I'm sure you might have recognized, we would predict a decrease in entropy because we're reducing the number of gas molecules. We've got 1 nitrogen and 3 hydrogens. We've got 4 molar gas molecules equivalents on the left-hand side, but we've only got 2 gas molecules on the right-hand side. So we would predict that that would actually be a decrease in entropy. It's getting more ordered. And then the third one, we would predict an increase in entropy. Again, looking at the moles of gas that are produced. 2 gas moles on the left-hand side for a total of 4 plus 1 for a total of 5 gas moles on the right-hand side. More complex, we're getting more molecules, 2 molecules to 5 molecules. You can think about the bonds, you can look at the bonds in the molecules, you can look at the bonds between the molecules. More bonds that are available, more microstates that they can exist in, the more disordered they will be. But that concludes us for today. What do? We predict and explain the sign of the entropy changes that occur during a change in state, during a temperature change. So looking at both of those on our diagram there. And then we looked during a chemical reaction in which there is a change in the number of gaseous molecules, where we said more gaseous molecules will increase the entropy, less will decrease it. Excellent. As always, tasks for you to pause, consolidate, 1 column at a time, bottom to the top. Thank you very much. Look forward to seeing you next time, where we'll continue our look into entropy as a concept. All the best.